We discuss in this video about probabilistic modeling. This is very useful in situations where the system may evolve into several different configurations. Many people find probabilistic modeling somewhat counterintuitive. A famous example of this is the Monty Hall problem. So far in the course we had deterministic models, meaning that we had a precise sequences of actions, precise effects, and it was only a matter of putting everything together and reasoning about the outcome. But what if at every stage of the modeling there are several options of how to continue? And we have to evaluate which options are available, what's the probability of each option, choose one according to some probability distribution. In this case, the system will have more than one future and several evolutions are possible. And the probability of each option might change as the system advances. Here is an example. We have a simple weather model and we only have two states for the model, sunny and rainy. And in this model, the weather for tomorrow depends on today's condition as follows. If today is sunny, then there is a 90% chance of tomorrow also being sunny, and 10% of it being rainy. If today is rainy, then there is a 50% chance of tomorrow being sunny and 50% of being rainy. And we can summarize the probabilities in the following transition matrix. So from sunny to sunny, meaning from sunny today to sunny tomorrow, we have a 90% chance, and from sunny today to rainy tomorrow we have 10%, and the same thing from rainy today to the different situations for tomorrow. It's also useful to represent this data in a graphical form like this, where the same thing is shown but in a different form. So you see now in a visual way, if today was sunny, then there is a 90% chance that tomorrow is also sunny, and so on. We will show this through some arrow or some transition in this plot. In fact, we can even remove the explicit representation of today and tomorrow and think about our model as having only two states, sunny and rainy, and think about the transition between the two states. The idea is, of course, that a transition will also implicitly mark the passing of one day, so the information about time is implicitly in the model. The transition matrix gives us the probabilities of changing the state from sunny to rainy. And the transition probabilities only depend on the current state, not on the past states. In other words, our model really depends for tomorrow. It only depends on how the weather was today and not really on how the weather was yesterday or last week. And we will be interested in asking questions like, if today is sunny, what's the probability for tomorrow? And that's easy to answer directly from this plot, but we will also want to know about the prediction for 10 days from now and even in average over a longer period of time. So let's see how to use this model. Let's say that today is sunny, and this is in fact because we see it outside. So today's probability distribution is 100% sunny and 0% rainy. And we mark this through the current state of the model, marking the probabilities of the two states. So I'm going to write x0 is 1 and 0, and this means that really 100% we are sure that it's sunny outside, and rainy is with 0%. Tomorrow, obviously, the model clearly says that it's going to be 90% chance of being sunny and 10% chance of being rainy. And this in fact can also be calculated as a multiplication of the current state with the transition probability. So we can also write it as 1, 0 times the matrix 0, 9, 0, 1, 0, 5, 0, 5. But this will be clearer now when we think about the next state. So we are not sure how it will be tomorrow, but there is a large chance that it will be sunny and some chance of it being rainy. And we just calculated these probabilities. So we know that today is sunny. So that's today. And tomorrow, meaning plus 1 day, there is a chance, in fact a big chance, that it's going to be sunny, 90%. And there is a chance of this being rainy. maybe it's better to write just 0.9 here, and then there is a chance of 0.1 to be rainy tomorrow. For the next day, obviously there will be a probability distribution between sunny and rainy. If tomorrow is sunny, then there is a 90% chance that the following day we also have a sunny day. If tomorrow is rainy, then there is a 50% chance that the following day will be in fact sunny. So really the chance of the next day to be sunny is 90% of the probability of tomorrow being sunny plus 50% of the probability of tomorrow being rainy. This is exactly what the multiplication of the vector state with the transition probability matrix will give us, helping to deal and to quantify the increasing uncertainty about the future states of our weather model. A similar thing also holds for the rainy state. We have a 0.1 chance coming from a sunny day and 0.5 chance coming from this one. So, in other words, the probability distribution for this day is going to be x1 times the probability distribution transition matrix, and that's going to be also, if I recognize that x1 is x0 times p, is going to be x0 times p squared. So in general, after n days, the probability distribution is going to be following the same kind of reasoning. Is going to be xn is whatever probability distribution we had the previous day times the transition matrix p, and this is going to be x0 times p to power n. So this reasoning also helps us make now a prediction of how many days are sunny over a longer period of time. We talk in this case about some concept similar to that of a steady state or an equilibrium, where the distribution between sunny and rainy is constant. In other words, we are talking about some probability distribution that we want to identify, where q times p is equal to q. So this we can solve, and we are going to find out that the probability distribution we are looking for is 0.833 and 0.167, and the way to read this result is that we can make a prediction according to this model that in the long term 83.3% of the days are sunny. So this is the probabilistic world. A word of warning is needed at this point. This is a world that offers very powerful tools to handle uncertainty, very useful in practice. But it's also a world governed by strange, sometimes non-intuitive behavior caused by accumulating uncertainties. I will not discuss it in this video, but I do advise you to search online the famous Monty Hall Problem and try to understand the behavior it describes. Other non-intuitive examples exist as well. For example, the birthday paradox that shows that in a room of at least 26 random people, there is a chance of more than 50% that two of them have the same birthday, even though there are of course 365 days in a year. I take now another example inspired by the US election system. All the values in this example, meaning the tendency of switching party loyalties, are of course completely artificial, leading to artificial predictions as well. Its point is only to demonstrate how to build a probabilistic model and not to give any realistic predictions about the US elections. So we are going to assume three groups: Republicans, Democrats, and Independents, and the problem is going to be for us to identify the long-term behavior of voters in a presidential election. And here are our assumptions. The data collected over the last 10 years shows the following average trends in voting. If in the last election somebody voted Republican, then in the next election there is a chance of voting still Republican 75%, voting Democrat 5%, and voting Independent 20%. If in the last election somebody voted Democrat, there is a 20% chance of voting Republican in the next election, 60% of voting Democrat, and 20% of voting Independent. And finally, If in the last election somebody voted for independents, there is a 40% chance that in the next election they will vote Republican, 20% for voting Democrats, and 40% of voting independents. The same thing can also be written in this graphical way, where we are representing by arrows the tendency from one election cycle to the second election cycle, and we write on top of these arrows the probabilities of each one of these transitions. We can formulate a model about the tendency of party loyalties over a long period of time as follows. If we denote by Rn percentage of voters to vote Republicans, and that's in election N. And we denote by Dn the same thing but for Democrats, and by In the same thing for independents. Then we can write a model like this. In the next election, we will have for Republicans, according to our model, we are going to arrive with 75% of those who voted Republicans last time, so it's going to be 0.75 times Rn, plus we are going to get 20% of those who voted Democratic in the last election, so it's going to be 0.2 times Dn. And we also get 40% of those who voted independents in the last election. A similar thing for Democrats, Dn plus 1 equals, we retain 60% of those who voted Democrats last time, and we get 5% of those who voted Republicans last time, and we also get 20% of those who voted independents last time. And finally, we can write for independents, they will retain 40% of those who voted independents last time, and they will get 20% of those who voted Republicans last time, so 0.2 Rn, plus they will get 0.2 of those who voted Democrats last time. So we can plug this model in some standard spreadsheet calculator, and we can observe the long-term behavior of this model, which looks like this.